Hey guys, so today we're talking about the different types of acid-base reactions. So yesterday you kind of got the introduction, get the feel, the pH scale, what all that means. Today we're going to talk about the, again, the two different types. Okay, the first one is the Bronsted-Lowry reaction. Okay, so Bronsted-Lowry reactions. This was actually the second type that was found. Um, and so it was two different scientists doing research at the same time, but not together. So they were doing this independently, and they came up with the answer at the same time. But this is basically adding on to the first type of reaction that we're going to be talking about in a second. Okay, but this first kind that we're talking about, Bronsted-Lowry, defines an acid as a proton donors and bases as proton acceptors. Okay. Remember that H is considered a proton, not the element hydrogen, like whenever you see the H plus sign. Okay, because hydrogen only has one proton and one electron. And if it has a plus sign, that means it lost the electron. So it's a floating proton, essentially. Okay. Um, Here's what it looks like, not in a compound, but just using letters to represent it. So here's the H in the acid. Okay. And it gets donated to the base. Okay, so this donates, that's the acid, to the base where it accepts it. All right. Um, to determine whether a substance is an acid or a base, you're going to count the hydrogens on each substance before and after the reaction. If the number of hydrogens has decreased, that substance is the acid. Okay, so here from, sorry, I got ahead of myself. Okay, and then if the number of hydrogens has increased, that substance is the base. It's accepted the proton. Okay. Um, these definitions normally talk about what's on the left side, and then the right side we'll talk about in a moment. Here we go. The substances on the right side of the equation are called conjugate acids, conjugate, and conjugate base. Conjugate means that a substance is formed, but it can be reversed. So it's the conjugate acid that can go back to the way that it was. It's the conjugate base that can go back to the way it was. Okay, so think of these reactions as being two ways. All right. So looking at the original equation, let's use these definitions to identify the conjugate acid, or the acid, the base, the conjugate acid, and the conjugate base. Okay, so let me change my colors up. Okay. All right, so what you're going to do for these is what I like to do is I have an A here on the left side of the arrow. I have an A here on the right side of the arrow. So I'm going to put the two compounds with A's in a box. Okay. I have a Z right here. I have a Z right here. So I'm going to make these two circles. Okay, boxes and circles. Right. If it's on the left side of the arrow, then it's either the acid or the base. Okay. If it's on the right side of the arrow, then it's the conjugate acid or the conjugate base. The word conjugate only applies to things on the right side. So as far as the left side goes, if the hydrogen decreases, that substance, the acid, well, we have hydrogen here, but we don't have hydrogen here. So it's decreasing as we go left to right. So that means the HA is the acid. Okay. So this is the acid. Let me write that in a darker color for you. Okay. Here it starts as Z and then it goes to HC. So this is actually increasing the hydrogen. Okay. So that means Z by itself is the base. All right. Then for the conjugate acid, okay, right, so if we have an acid here in this square, that means that the A on the other side, that's going to be the conjugate base. I'm just going to say C base. Okay. So the A minus is my conjugate base. And then the HZ plus, okay, that's going to be the C acid. So right now I'm confused with the way I described it. So let me break it down just a little bit more to say why I did what I did. Okay, so hopefully you understand why I chose to pair up the HA and the A and why I chose to pair up the Z and the HZ. Okay, if it's on the left side of the equation, it's either the acid or the base. Generally, it's the one that starts with more hydrogen is the one that's the acid. Okay, the one that starts without hydrogen or with less hydrogen is the base. All right, once you identify the acid and the base, all right, when you look at the partner on the other side of the equation, okay, the acid is always paired with the conjugate base. The base is always paired with the conjugate acid. Okay, so if you want to write that down, acid goes with the conjugate base. And the base goes with the conjugate acid. Okay. This, again, can be kind of confusing, so I've got a lot of practice problems for us to do together. Okay, so when you see something like this, the question's going to say identify the conjugate acid or identify the base or just identify something. All right. So when you see these kind of questions, I want you to partner up. Okay. So here we have Cl. And do we see Cl or HCl? Do we see Cl on the other side? Yes, we do. So I'm going to pair these up by boxing them in. Okay. Here we have NH3. Here we have NH4. Those look really similar too, so I'm going to circle those in. Okay, so now I have my two pairs. All right. Remember that the definition of an acid is the pair that, or is the one in the pair that loses or decreases in hydrogen. Okay, decreases in hydrogen. So this goes from HCl down to Cl. Okay, so this is decreasing. So this is on the left side is the acid. Okay, so we'll say A for acid. And the acid is always with the conjugate base. So that means that the Cl is going to be the conjugate base. So Cl minus. All right, we've got two of them figured out. Here we have NH3 and it changes to NH4. So it's increasing in hydrogen. So that means NH3 is the base because it starts with less hydrogen. And that NH4 plus is the conjugate acid because that's the one that has the increased hydrogen. All right, so base, conjugate acid. All right, remember that base is always paired with a conjugate acid. All right, so I'm going to do one more example with you, and then I want you to pause the video and try it on your own. Okay, so we have H2SO4 plus H2O makes HSO4 minus and H3O plus. Okay. So what do you think we're going to pair up? Okay, we have SO4 here, SO4 there, so we're going to pair up the SO4s. And then we have H2O and H3O. Those seem pretty similar, so I'm going to pair those up too. Okay. So looking at the first pair, it is from the left side to the right side is decreasing in hydrogen. So that means the left side is the acid and the right side is the conjugate base. And I realized I wrote acid in the acid blank. H2SO4. Okay. H2O to H3O plus is increasing in hydrogen. So H2O is our base. H3O will be the conjugate acid. Okay, so H2O, H3O plus. All right, if you're feeling pretty good on this, pause the video, try these last two on your own. Okay. If you're still kind of hesitant, then let's at least do the pair up and then pause the video. Okay, so for the pair up here, we have HNO3 plus CH3OH makes NO3 minus plus CH3OH2. Okay, so HNO3 is going to be paired up with NO3. CH3OH will be paired up with CH3OH2 minus. Okay, again, if you're getting confused on the pairing up, we're pairing up what looks very similar. They might just be different by one hydrogen. Okay, so if you're feeling comfortable now, pause it, try to identify which one's the acid on the left side, and which one's the base, and then you can figure out the conjugate acid, conjugate base. All right, so looking at HNO3 to NO3, this is decreasing in hydrogen. Okay, it lost a hydrogen. So this is the acid, which means that this is the base. Okay. All right, and then with CH3OH to CH3OH2, this has increased in hydrogen, so this is the base. This is the conjugate acid, okay? All right, so at this point, try this last one all on your own, okay? Okay, so I have the answer up as I just worked it out. Now, if some of you guys are pattern people and you really like patterns, you've kind of noticed that the acids always seem to be first and the bases always seem to be second. It's not always like that. Just these sample problems that I picked out didn't have it mixed up. Okay, so always identify your partners. All right, and then which one's gaining, or sorry, which one's losing a hydrogen, which one's gaining, and that'll help you figure out the rest. Okay, now let's go ahead and start talking about the second type of reaction. All right, Arrhenius or neutralization reaction. All right, so Arrhenius defines an acid as a substance that dissociates in water to form, get my darker color out. to form hydrogen, thus increasing the concentration of hydrogen okay. Hydrogen. I didn't leave myself a lot of space. Or hydronium. Okay, so let me restate this one. Arrhenius defines an acid as a substance that dissolves in water to form hydrogen ions, thus increasing the concentration of hydrogen or hydronium in a solution. So this is more of like what we were talking about yesterday with the acids. Okay, this is the original definition of an acid. All right, that like hydrochloric acid releases hydrogen ions. All right, an Arrhenius base is a substance that dissociates water to form hydroxide ions, thus increasing the concentration of hydroxide ions in a solution. Okay, remember OH is hydroxide. So again, yesterday we talked about acids have an H plus or hydrogen ion, and hydroxide has OH minus. Right, this is the general, the original rule. Arrhenius acid-bases reaction are also known as neutralization reactions. All right. Here's what they look like. Okay. When you put an acid together with a base, it forms salt and water. That's what it means by neutralization. Okay. Let's look at the examples. The best way to explain it. Okay. So for the first example, we have hydrochloric acid, which is a super strong acid with a pH of like 2. Okay. Then you have sodium hydroxide, which is also a very strong base, has a pH of like 12 or 13. Okay, when you put hydrochloric acid and sodium hydroxide together, the chlorine and the sodium come together to form sodium chloride, and then the hydrogen and the hydroxide come together to form water, and you're literally left with salt water. Okay, like that you could gargle in your mouth. It is neutral, so it no longer poses a danger to you. All right, that's what it means by neutralization. You take an acid with a low pH and a base with a higher pH, and when you put them together, it kind of averages out and makes it a neutral compound. Okay, so to work these kind of problems, what you're going to do is you're going to take the hydrogen and the hydroxide, and you're going to rewrite that as water, as H2O. Okay, so we took the hydrogen and the hydroxide out, found it as water. And it can go in either blank. I'm just choosing to write it in the second blank. All right, then we're left behind with potassium and bromine. Okay, if it's written first here, it needs to be written first in the blank. Okay, and by written first, I mean when it's together in the compound. See how potassium's first here and bromine's second there? So that means bromine will be written second here and potassium will be written first. Okay, do not say BRK. Okay, that will be wrong. Okay, K goes first, then the BR. Metal always goes first. All right, but when we do that, we get potassium bromide, which is a salt. Salt, by definition, is when a metal and a nonmetal come together. Okay, so here's our salt, here's our water. It's a neutralization problem. Okay, so looking at example 3, again, we're going to do the same thing. We have hydrogen here, we have hydroxide here. So those are going to come together to make water, and I'll just write H2O here to show that it doesn't matter where you write the H2O. And that leaves us with calcium and sulfate. Okay, Notice how we have the 2's right here? That's because sulfate has a -2 charge and calcium has a +2 charge. So we kind of got to jump back to nomenclature right now. When we bring them together, we're going to have calcium first because it was written first with the hydroxide, has its +2 charge. And then we have sulfate, okay, which was written second, so we write it second, which has its -2 charge. If they both have the same charge, what did that mean? It means that we can cancel out our charges. So that's going to leave me with the salt of calcium sulfate. Okay. See how far you can get on this third exam or on this last example. All right, I'll put the answer in just a moment. All right, so that leaves us with NaNO3 or sodium nitrate plus water. Okay, so that's our result. Notice again, water is always one of the products. Okay, and then whatever elements you have left, that's what comes together. All right, you'll always write the metal first, which is usually first in the compound, or which is always first in the compound anyways. And then you write the non-metal parts second. Okay, before you get started on the knowledge check, the main thing you need to see, okay, the reason that this is not the only definition of acid-base reactions, okay, is because with these, we don't always have hydroxide present, but we do have the hydrogen proton moving around. So that's why this second definition came about. So they both have to do with proton donors, okay, or with both of them donating the proton. All right, but one of them, like, that's the only thing that it's talking about, which is the Bronsted-Lowry. And the other one that we just did, the donor is making it into a water molecule. Okay, so I pretty much just helped you with that first one there. Okay, a proton donor best describes the Bronsted-Lowry. All right, and then I'll let you go ahead and finish the rest of this on your own. All right, if you have any questions, ask your teachers, but thank y'all for listening and working through these notes today.